Hi, this is Mr. Asher, and this is for Chem 121. And I'm going to work through a couple of examples for looking at limiting reagents, okay? And, and so first we're going to look at a really simple reaction, which is this one, 2Cr plus 2H3PO4 goes to 2CrPO4 plus H2. And we can see right away this is a redox reaction because we've got chromium in its elemental state going to chromium plus 3. So we have chromium 0 going to chromium 3 plus 3 electrons. And we can see that hydrogen is being reduced because we have H plus 1 electron, well, 2H plus 2 electrons going to H2, right? So it's a redox reaction, which is useful to know. Now, the other thing we notice is that the stoichiometric coefficient on front of chromium is 2, and in front of phosphoric acid it's 2. And that means that the stoichiometric ratio for chromium to phosphoric acid is 1:1, meaning for each mole of chromium we use 1 mole of phosphoric acid, right? So just thinking about it very simply, if I had 2 moles of chromium, I need 2 moles of H3PO4 phosphoric acid. Okay. If I have 0.31 moles of chromium to react all that, I need 0.31 moles of H3PO4, right? So what's really going on here is there are conversion factors around, and we can get those from the stoichiometry. But first off, I just want to make sure that it should be clear that when the stoichiometry is 1:1, that it's really easy to figure out or it should be relatively easy to figure out the limiting reagent. Let's say I had 0.5 moles of chromium and 0.75 moles of H3PO4. Okay. How many moles of chromium of H3PO4 do I need to react with that much chromium? Well, I need 0.5 moles of H3PO4. PO4. And how many moles of chromium do I need to react with that? Well, I need 0.75 moles of chromium, right? And so clearly this is less than this because it's 1:1. So that means that chromium is limiting, right? And if I let this reaction go, I'll have excess for phosphoric acid left over, H3PO4. How much will I have left over? Well, we can figure that out by looking at that the amount of phosphoric acid I start with, 0.75 moles of H3PO4. And I can subtract off the moles of 0.5 moles of chromium. But now here's where there's a hidden thing in here, that there's a conversion factor between moles of chromium and moles of H3PO4, right? These really don't have the same units. It's as though I'm trying to subtract a green apple here from a red apple here, right? And the two aren't the same. So I need a conversion factor, and that's given by the stoichiometric coefficients, which tells me that I need 2 moles of H3PO4 for 2 moles of chromium, right? And so now the moles of chromium are canceling with the moles of chromium. And what's 2 divided by 2? Well, it's 1, right? So it's just 1:1. And so I can just subtract 0.75 minus 0.5, and that gives me moles of H3PO4 left over, which is 0.25 moles of H3PO4. Now, if I'm trying to figure out how many moles of chromium phosphate, 2CrPr4, I'm going to form from that, right? So that I would do that as, okay, so I'm going to use up all my chromium. So moles of CrPO4 is going to equal moles of chromium times the stoichiometric conversion factor, which is 2 moles CrPO4 per 2 moles of chromium, which again is 1-to-1, which means that the moles of of chromium phosphate, CrPO4, is going to equal moles of chromium I started with, which is going to equal 0.5 moles. Right? In other words, that's the stoichiometric conversion factors are working pretty well in this because everything is 1-to-1. Now, suppose that I wanted to know how much hydrogen I was going to produce from that much chromium. And there it's a little different, but not all that much more challenging. So the moles of hydrogen, H2, is going to equal moles of chromium because that's the limiting reagent. At the end of the reaction, I'm going to have no chromium left over. All got converted to chromium phosphate. It's going to be moles of chromium times moles of H2 per moles of chromium. And there, the stoichiometric coefficient is moles chromium times 1 mole hydrogen divided by 2 moles chromium, right? So it's a half. So if I started with a half a mole of chromium and it all got converted, I'm going to have 0.5 divided by 2 moles H2, and that's going to be equal to 0.25 moles H2. Okay. Now let's look at a reaction with a little bit more complicated stoichiometry. And let's look at P4 plus 5O2 goes to P4O10. Okay. And so now let's look and see, and suppose we have 0.200 moles of P4, and we have 0.98 moles, 980 moles of O2, which is the limiting reagent in this case. Well, now our stoichiometric coefficients aren't 1-to-1, they're 1-to-5, and so it's maybe a little more confusing. But we could approach it the same way we did before, and let's predict how much oxygen we would need if for 0.2 moles of PO4. And in that case, moles, theoretical, we're going to call moles of oxygen is going to equal moles of P4 times moles of O2 per mole of P4, right? And so putting numbers into that equation, we're going to have 0.200 times, and there are 5 moles of oxygen per 1 mole of P4. And this is moles of P4 here. I have to write the unit down, right? So this cancels, and this comes out to be 5 times 0.2 is 1.00 moles of O2. Okay. So is this number here greater than this number here? Yes, and that means that there isn't enough oxygen in our system to react all of that P4, right? Because this number here is larger than that number here, there isn't enough oxygen to react all of the P4, and that means P4 is limiting in this case, right? Okay. And that if the reaction, and that if we burn off all of this I'm sorry, there isn't enough oxygen. Oxygen is limiting. What am I saying? That because, let me back up a minute, that this number here to react all of this phosphate, right? It would require one mole of oxygen, 1.00 moles of oxygen, but we only have 0.98 moles of oxygen, meaning that oxygen is smaller than the amount required. So oxygen is limiting. So oxygen is limiting. O2 is limiting. Right? So at the end of this reaction, all the oxygen is going to be gone. We've reduced some P4O10, but we've got some P4 left over, right? Because all of the oxygen got used up by reacting with the P4. So how do we figure out what the how much P4 is going to be left over in this case, right? So now we have to figure out, okay, well, how much oxygen will react with, how much P4 will react with this much oxygen? So we want to know moles of P4 that will react with 0.980 moles of O2, right? And for that, we can use a stoichiometric coefficient, which is 1 mole P4 over 5 moles of O2, right? So these are going to cancel. And then we're going to have 0.980 divided by 5 moles of P4. And that's how much phosphorus, P4, is going to be reacted by 0.98 moles of oxygen. And we divide that by 5, and we get that equals 0.196 moles of O2. So how much P4 is going to, sorry, moles of P4, not moles of P2. Moles of P4. So how much P4 is going to be left over? Well, it's going to be 0.200 minus 0.196 moles of P4 left over, which is 0.004. Right? Okay. Now, how much P4O10 do we form? Well, how much P4O10 we formed is related to how much P4 react, right? And it's 1-to-1. So if we make, right, there's a coefficient of 1 out here and 1 out here. So that means for each mole of P4 that we react, we get 1 mole of P4O10. So that means that moles of P4O10 will equal 0.196 moles, because that's the amount of P4 that we react from all of that. From all of that, that's the amount of oxygen. That's the total amount of P4 that will react with that much oxygen, right? So as you get better at these, you'll be able to look at these. Normally, these coefficients are small ratios, and you can look at things and go, oh, well, if I need 3 times more oxygen than I've got, whatever that is, then that's not enough oxygen, right? So that's how you do those. Now let's take a look at a couple of the problems I assigned, and let me pause for a minute to get those screens up. Okay, so let's look at one of the questions from the homework. And this is question number 1 from part 2 of module 5. So this is module 5, part 2, question 1, right? And the reaction is 3 sodium bicarbonate, NaHCO3, plus citric acid, H3C6H5O7, goes to 3CO2 plus 3H2O plus sodium citrate, Na3C6H5O7. And see, this is an acid-base reaction because you have the acid here reacting with the base here to form, well, carbon dioxide comes off with water and then the salt of the acid, sodium citrate. So that's an acid-base reaction. And the problem gives you a range of concentrations. So we'll just use 0.014 moles of NaHCO3 and then 0.039 moles of H3C6H5O7. Okay. And it asks us which is the limiting reagent, which is the excess reagent. Okay. Well, the stoichiometric ratios between bicarbonate and citric acid, you need 3 times as much bicarbonate as you need citric acid. So let's take a look at how much bicarbonate, how much citric acid we're going to need to react with that much bicarbonate. So moles, and I'm just going to abbreviate citric acid as Ca, is going to equal 0.014 moles of NaHCO3. And now I'm going to form the stoichiometric ratio times 1 mole of citric acid for 3 moles of NaHCO3. Right? So 0.014 times so now this is going to equal 0.014 divided by 3, and now moles of bicarbonate cancel out, and leaves us with moles of citric acid. So 0.014 divided by 3 is going to equal 0.014 divided by 3 is going to equal 0.0047 moles of citric acid. So this is the maximum amount of citric acid I can react with 0.014 moles of bicarbonate, right? And how many moles of citric acid do I have? Well, I have almost 10 times more than that. So the actual I have is 0.039 moles of citric acid, right? So that means that this is really much smaller than that. So that means that my limiting reagent is bicarbonate, right? Because I don't have enough, because to think about it another way, if I figured out the amount of bicarbonate I would need to react with 0.039 moles of citric acid, so moles of bicarbonate, NaHCO3, is going to equal 0.039 moles of citric acid times 3 moles of NaHCO3 to 1 mole of citric acid, right? So citric acid cancel, and this becomes 0.117 moles, I believe, right? Which probably for significant figures, we should abbreviate that or round that to 0.12 moles of citric acid. I'm sorry, of not citric acid, moles of bicarbonate, NaHCO3, right? So this is very much larger than the amount of bicarbonate we have. So again, you can see that to react all of that citric acid, 0.039 moles, we don't have nearly enough bicarbonate. So the amount of bicarbonate, so bicarbonate is the limiting reagent, right? And the excess reagent is citric acid. Now, how much limited reagent do we have left over when the reaction is complete? 0, because it all gets used. 0 for the limiting reagent. Right? And how much citric acid do we have left over? Well, as we do this again, and we would say, okay, well, this is the amount of citric acid we're going to use, and we subtract that from the amount we have. So it's 0.039 minus 0.0047, which is going to be equal to 0.0343, which we're going to round back to be 0.0343 moles. Right? And if we want to know how much sodium citrate we're going to form, then the stoichiometric ratio is 3 to 1. So we would divide the amount of this. It would be 0.0047. That's how many moles of sodium citrate this guy we're going to form, right? Because that's the stoichiometric ratio. So anyway, so that's how much you have left over, 0.034. Hopefully that's clear. I'm going to stop there. And if anybody has any other questions, they should send me an email. All right.